Hi class. We're going to finish our study of chapter 1 today in this video by talking about section 6.1 and functions. Now functions, really what it breaks down to is it's going to be new notation for something we've already been learning about, all right? These linear equations are actually functions. All right, so what we have today, our goal here is we want to decide whether what we call a relation, and I'll define what a relation is in a second, is a function and use function notation. Okay, so let's start with the definition. A relation is any set of ordered pairs. So if you remember, like in the linear equations we've been learning about in this section, ordered pairs are like the x comma y, like something like 2 comma 5. Okay, that's just a relation. What that means is the value x2 is related to the value y5. So 2 and 5 are related. There's a relationship between them. So a function, all right, is a specific type of relation where there is exactly one output. Okay, the outputs are the y for every input x. Right? So what I'm saying is for every x, there is exactly one y. What that means is in that example 2 comma 5, for the number 2, it is related to or maps to or is equal to through some relation only 5, only one value 5. All right, so each x goes to one y value. All right, so look at this example here. We have this x and y, all right, and I'm asking if this is a function. All right, so let me go back. So it is a function if every x goes to exactly one y. Well, look at this. This x here is saying, well, when x is 1, it maps to or goes to 6 and 7. So this x value goes to two y values. Over here, look at this one. 1 goes to 6. This is weird, but 2 also goes to 6. Well, this case here is not a function because this x value goes to two y values. Where over here, this x value goes to one y value. This x value also goes to one y value. They can even go to the same one. So this is a function. So each x, think about the arrow, only goes to one y. It's a function. But over here, this x had two arrows going to two different y values, not a function. Look at this equation. Y is equal to 2x. All right, if I want to know if this equation is a function, let me look at the xy chart, all right, and talk about the mapping for it. When I pick these x values, -2, -1, 0, 1, and 2, 2 times -2 is -4, and so on when you plug it in here. When you look at the input here to the output, here are my x value inputs. These are the output y values. And each x value goes to exactly one y value or maps to exactly one y value. So this here is a function. If we had a case where -2 pointed to two different values, it would not be a function. In general, anything that is of the form y is equal to mx plus b is a function. So this is y is equal to my slope, 2x, plus my b value here is actually 0. So yes, this is a function. All right, let's look at these absolute value things. All right, y is equal to the absolute value of x, and x is equal to the absolute value of y. Determine if these are functions. Well, look over here, setting up your x, y values, -2, -1, 0, 1, and 2. Does each of these x values map to only one y value? Well, look at the input to the output. Does each x have only one arrow going away from it? Yes, it is a function. So even though -1 goes to 1 and 1 goes to 1, different x values can go to the same y value. That's okay, but it can't happen the other way around. So here I'll actually pick the y's first. So absolute value of -2 is 2, and so on like this. When I look at the mapping, my x, my inputs, to my outputs, I only have two inputs. There's only the values 0, 1, and 2. And when I look at the different outputs, look what happens. 1, x goes to -1, and 1 also goes to 1. and 2 goes to negative 2 and 2, this is not a function because an input, an x value has 2 arrows going from it, so not a function. All right, another definition. I want to talk about the domain and range of a function. The domain of a function is the set of all input x values, all right? So the domain is the input or the x values. And the range of a function is the set of all outputs or y values. All right, so let's identify the domain and range, then tell if the relation is a function. So I have these inputs to these outputs. Notice how the 3 goes to negative 3 goes to 3, 1 goes to 1, 3 goes to 1, 4 goes to negative 2. The domain is the set of all the inputs. So the domain is the input values, negative 3, negative 1, 3, and 4. That's the domain. And it gets these set notation bracers here. The range is the set of all outputs, all right? So it looks like the outputs starting from the lowest is negative 2, 1, and 3. And this, is it a function? Yes, each input is mapped onto exactly one output. All right, let's look at another one here. So I've got this input, and I'm mapping this way. All right, so negative 3 goes to 3, 1 goes to negative 2, 1 goes to 1, 4 goes to 4. So the domain, keeping that set notation, is the values of the inputs, so negative 3, 1, and 4. And the output here is 3, negative 2, 1, 4. So is this a function? No, because the input 1 is mapped to negative 2 and to 1. All right. Let's talk about the vertical line test for functions. All right, so you got this graph here. The vertical line says if any vertical line can pass through a function, or if any vertical line passes through a graph more than once, all right, it is not a function. If it passes through a graph at only one point, it is a function. So suppose I have this graph here. Is this a function? Well, watch as I do a vertical line through it. Oops, sorry about that. The vertical line, going back to this, any vertical line will only go through it once, so it is a function. This line here, any vertical line will only go through it once. It is a function. This one right here, no, this is not a function because a vertical line will go through it an infinite number of times. You can see the blue line on top of it, so it is not a function. Here, any vertical line will go through it only more than once. This is a function. Over here, go through a vertical line. It'll go through this vertical line here. We'll hit it more than once. This is not a function. Here, vertical line will go through it only once. It is a function. Here, vertical line goes through it, hits the graph here 1 and 1. This is not a function. Here, vertical line goes through it only more than once, or goes through it more than once. This is not a function. So that's another way you can just look at a graph and tell if it is a function. All right, let's look at these. All right, determine whether they're a function or not. Here are the inputs, 0, 1, 2, and 3. Each one of these inputs goes to the value 5. Oh, interesting. Well, yes, this is a function because each input only goes to one output function. Down here, negative 3 goes to negative 1. Negative 3 also goes to 0. Negative 3 goes to 1. Negative 3 goes to 2. Notice how the input, negative 3, goes to 4 different values. So down here, it is not a function. Here, vertical line goes, hits it more than once. This is not a function. On this one, I'm saying negative 2 goes to 3 and 4. Negative 1 goes to 5. And 0 goes to 6. Well, this right here, this is not a function because negative 2 goes to both 3 and 4. All right, so we have some idea of what a function is. Now let's talk about function notation. All right, function notation is read as what's called f of x. So the x here is the input, and the output, what we're doing here is we're changing y to what's called f of x. We're saying, hey, look, we know that this ordered pair xy is this function notation, or is this function, so it gets this special notation, f of x. And it just looks like this. It's just another way of saying y. This is not f times x. Okay, this is saying, hey, look, our relation between x and y is a function of x, or y depends on x. We just replace y with this notation, f of x. All right, let's look at an example here. This linear equation y is equal to 2x plus 3. All right, we know that y is equal to mx plus b is a relation. So I'm just going to change y and call it f of x. So when x is equal to 1, what is y? When I plug 1 in, I get 2 times 1 plus 3. It's 5. And so on. When x is equal to 2, 2 times 2 is 4 plus 3 gets me 7. Notice how when I told you what x was, you literally just plugged it into the equation. And so on. When x is equal to 3, 2 times 3 is 6 plus 3 is 9. And when x is equal to 4, 2 times 4 is 8 plus 3 gets me 11. Now notice here, I'm saying, what is f of 1? Well, here I'm telling you x is equal to 1. So I'm literally going to plug 1 right into the equation. So 2 times 1 plus 3 gets me 5. So notice what I did there. Whenever there's something inside here, you're just plugging it into the equation. F of 2, well, replace the x with 2. 2 times 2 is 4, plus 3 gets me 7, and so on. Just like that, just like over here. So notice how f of x is just another way of calling y. That's all it is, literally all it is. Now when I say what is f of negative 4, notice how it's not over here. Well, I'm just going to replace negative 4 in for x. So 2 times negative 4 is negative 8. Negative 8 plus 3 gets me negative 5. That's all I did there. All right, let's look at some more complicated ones. Suppose I give you two functions, right? Notice these ones I call them differently. In the previous example, I called the function f. Actually, you can call it whatever you want, all right? So this one, the function is g of x, and this is the function h of x. Just different names meaning the same thing. We have a functional relationship. So when I want to find g of 4, we'll plug 4 in for x. 4 squared gets me 16. H of negative 2. Well, now I'm going over here. 3 times negative 2 is negative 6. Negative 6 minus 2 gets me negative 8. G of 3. G of negative 3, excuse me. We'll plug in negative 3 here. Negative 3 squared gets me positive 9. H of 5. 3 times 5 is 15. Minus 2 gets me 13. All right, these ones over here, just follow the algebra. H of 4 plus g of 1. Well, what's h of 4? H of 4 is 10. 3 times 4 gets me 12 minus 2 is 10. Plus g of 1. 1 squared is 1. 10 plus 1 here just gets me 11. Now here I'm multiplying. H of negative 5. Well, when I plug negative 5 into here, I get 3 times negative 5 is 15 minus 2 gets me minus 17. Now I got to find g of negative 2. When I plug negative 2 in here, I get 4. And minus 17 times 4 gets me minus 68. All right, h of 3. This is weird. This is g of comma h of 3. We'll figure out what's inside here. What's h of 3? H of 3, 3 times 3 is 9, minus 2 gets me 7. So I found out what the inside part is. Now g of 7, well, what's 7 squared? 7 squared is 49. Another one, just for practice. H of g of 2. We'll find out what's the inside. G of 2. G of 2 gets me 4, because 2 squared is 4. H of 4, 3 times 4 minus 2. All right, well, 3 times 4 is 12, minus 2 gets me 10. All right, so let's evaluate this function over the domain, okay? So I'm telling you the domain, the inputs is negative 1, x is 0 and x is 2. Well, f of x is equal to 4x. So what I've got to do when I say evaluate over the domain is take -1, plug it in here. Take 0, plug it in here. And take 2 and plug it in here. When I do, -1 in for x, 4 times -1 is -4. 4 times 0 is 0. 2 times 4 is 8. And you can go on and see what the rest. Plug in -1. 3 times -1 is -3. Minus 9 gives me -12, and so on. The same thing down here. Plugging -1, 0, and 2 in for x here produces 0, -1, 3. All right, let's graph this linear function next. All right, so now I'm telling you f of x is equal to -x plus 3. Well, remember what this is. F of x is just another way of saying y. So when I'm going to set up my table here, I'm going to pick some values for x. This one I picked a bunch. And normally you'd see y here, but this I'm just saying is f of x. So when I plug in -3 into this, I get -3 is 3, plus 3 gets me 6, and so on. You can see the rest of these here as I plug them in. Now I'm going to graph these as ordered pairs. So I'm going to set up my axis here. And now this here, the horizontal axis is always the x-axis. And instead of it being the y-axis, we're just calling it the f of x axis. Just another way of saying y. So I'm going to plot these points. I'll just plot these. So -2, and then f of x is 5. -1 and 4. 0, 3. 1, 2. 2, 1. And 3, 0. And now I can draw the line through these points. And this is just the graph of this function right here. All right, let's do 2 more examples where I give you a graph. All right, so look at the graph of f of x. So I'm saying this is the graph f of x. What is f of -3? All right, well, what I'm saying is I'm plugging in -3 for x. So here's -3 for x. What is the value of f of x? I'm going to scroll down. Look, it's right here. It's -8. So when x, the input, is -3, the value of the function is -8, like this. Let's do another one. Look at the graph of f of x here. Okay, what is f of 6? Well, in this case, go over to 6 for x, and then look down at the graph. Where does it hit? This one is also -8. So this graph is telling you what all the ordered pairs are, like so. All right, class, that is our introduction to functions.